Hi, my name is Michael Sandel and welcome back to Calculus. Today, section 2.2, the limit of a function and limit laws. Okay, so we are going to have some big fun here. We're going to do some things that may seem a little bit strange, but I promise it's getting us somewhere and it does some really cool stuff. So anyway, let's get started. Let's start by considering this function that I have on the board, and you can see I've got a graph over here for it. We'll look at that in just a minute. The function is f of x is equal to x squared minus 4 divided by x plus 2. Now, importantly, the function does not exist if x is equal to negative 2, right? Because if you take negative 2 and plug it in, negative 2 plus 2 is 0. You can't divide by 0, so it doesn't exist there. So anyway, the graph ends up looking something like this. Long story short, we could, if we wanted, factor the numerator here, reduce the fraction, and then graph what's left. The difference is, though, we still have to leave this hole at negative 2. So you can see I have a graph. All right, so the idea behind a limit is this. We're trying to figure out what the function, where the function is going as x gets very, very close to, in this case, we're looking at negative 2. I'll label that. So as we get really, really close to negative 2, what happens? Okay, and so the idea is, if we think about, I'm going to draw this kind of rectangle around x equals negative 2, what y value do we get as we squeeze in on that x value? Okay, that's kind of the idea. Now, we're going to make this a lot more rigorous here in just a minute, but it's a really very, very important concept here. We're going to take this and we're going to squeeze in on this x value, which will then squeeze our y values to give us the limit. That's kind of the basics of this. Like I said, a lot more rigorous in just a minute. Now, importantly, the function does not have to exist at the x value in order for the limit to exist. That's going to be fun. So basically with this one, the limit's going to end up being negative 4 because that's really where this graph is heading. And like I said, we'll make this more rigorous here in just a second. But so the limit exists, it's negative 4, but the function doesn't exist there. And so that's going to be a little weird, a little goofy, and let's get to the next board. All right, so here we go. We have here kind of a definition of a limit. It's an intuitive definition. We'll get a very rigorous definition later in the chapter. For now, here we go. And you'll notice it took the entire board. So yeah, this isn't going to take long on this board. If f of x is defined on an open interval c about the point x is equal to c. So on that example that we had before, our x value was negative 2 that we were looking at. Okay, except possibly at c itself. Okay, again, the function doesn't have to be defined at the number we're looking at. And f of x is arbitrarily close to the number L for all x sufficiently close to c. We say that f approaches the limit L as x approaches c, and we write it as the limit as x goes to c of f of x is equal to L. Isn't that fun? Again, what is this saying? Think back to that graph. If you need to back up the video and go look at that graph again. It's saying that if you can squeeze in close enough to that x value, that negative 2 that we had on that graph, that your y values squeeze in close enough to the limit, which in that example was negative 4. Okay, so again, if you need to go back and take a look at it, basically we're going to squeeze the x in order to squeeze the y. I said this earlier, and I'm going to say it again. You don't actually have to have a function there. Isn't that fun? Right? We had a big hole in our graph. So you don't have to have a function value at that point. You just got to be getting very close to something. Let's go on. Okay, so now we're going to establish limits for our first two really basic functions. And from these two, we're going to build up lots of other limits. So our first two functions are what's called the identity function, where f of x is just equal to x. Basically, whatever you put in, you get the exact same thing out. If you think about this graph, it's just a line, right? And it's a line with a slope of 1, right? Because every x value gives you the same y value. I didn't say that well. Every x value then pops out the same number for then its y value. So pick a c, doesn't really matter which one you pick here. Any x value you pick, the y value that goes with it is going to be the exact same thing. So what we can say about the identity function is that the limit of that function as x goes to any number is whatever that number was. If you want to take x to 2, you're going to get a limit of 2. If you want to take x to negative 16, you're going to get a limit of negative 16. So that one's really nice. The other one that's super nice is the constant function. F of x is equal to k. A constant, remember, it's just a number. So k here could be 7, could be negative pi, right? It's just a number. It's a constant, it's not changing. So you have a function equal to a number. Well, guess what? If your function is always the same thing, your limit is going to be that value because, well, here's a value of c. What y value do you have to be getting close to as you travel along this graph and pinch in on c? Well, it doesn't make any difference because every x value gives you the same y value. So every one of these is going to have that same y value of k. All right, so now what we're going to do is we're going to take these and we're going to use them to build up some other rules. We're going to have a theorem that's going to let us do lots of stuff, and we're going to use these as the basis then for what comes after that. So this theorem, you will find it on page 61 in your calculus book. It's theorem 1, the limit laws. I'll put them on the board here in just a second, and then we'll kind of start applying some of this stuff so that we can start building limits for much bigger, uglier looking functions. And yeah, there we go. All right, so now we're diving into these limit laws. Again, they're on page 61 in your book, so feel free to copy them off of there or to just flip back there anytime you want. I have the first few on the board. I ran out of room. All right, let's get started. If L, M, C, and K are real numbers, no imaginary numbers here. We are doing calculus with real numbers, much nicer. And the limit as f of x approaches, limit of f of x as x approaches c is equal to L. And the limit of g of x as x approaches c is m. So we have two functions with known limits. Okay, now this could be something that we tell you, and we just say, hey, we have this function and its limit is 7. Or it could be something that you already know, like, oh, I don't know, f of x is equal to x, and f of x is equal to k, right? Those ones that we just did. See, this is where the power is going to come in here. We're going to be able to start with those two little teeny nothing functions, and we're going to be able to do a whole lot of stuff with them. What can we do? First, we have a sum rule or a difference rule. They're the exact same thing, just change the plus sign to a minus sign. All right, it says the limit as x approaches c of f of x plus g of x. So again, we have these two functions. They both have known limits. Guess what? When you add them together, you add their limits together. We can do a constant multiple. The limit as x approaches c of k times f of x, where k is just this constant number. It could be 2, it could be 5/3, lots of possibilities. But a constant multiple is just going to let you do k times that known limit. A product, the limit as x approaches c of f of x times g of x. Again, here's these two functions with known limits. All we do is multiply their limits together, and you're probably thinking, wow, this seems really kind of intuitive. Yeah, a lot of it is, and that's going to be very useful for us, and it's going to make our lives way nicer than they might have otherwise been. So let's move on, and I'll get to the other limit laws on the next board. All right, last two limit laws. Quotient rule, the limit as x approaches c of f of x divided by g of x is just L over m. Again, those two limits divided this time, but we do have one little catch here. This only works if m is not 0. Still can't divide by 0. Just wait, that's coming. That'll be really fun. That's in chapter, I want to say 3. 6, powers. The limit as x approaches c of f of x raised to the nth power is the limit to the nth power, and there is one more. Roots, the limit as x approaches c of the nth root of a function is just the nth root of the limit. So here's the fun. That's a lot of stuff, right? We have sums and products and quotients and powers and roots, and I'm sure I left something out, but we have a lot of stuff. And what that means is, for a lot of kind of normal looking functions that we're used to seeing, we're going to be able to have some really fun little tricks to actually evaluate these limits. So let's start with a pretty simple example. We'll get some harder ones on the next board. But let's just find the limit of this one. The limit is x approaches c. So c is just some random generic number. It could be any number we want. Okay, maybe we leave it generic. Maybe in the homework you see it with a number there. Doesn't make any difference. Of x cubed. So we have the limit is x approaches c of x cubed. So here's how we're going to make this work. We know what the limit of x is. Right? We know that if you take the limit as x approaches c of the identity function, that you just get the number you're approaching. You just get c. And so since what we have here is a power, we can use that power rule for limits to just say, hey, we know the limit of x, so the limit of this whole thing has to be c raised to the third power. And that's it. Could do it with a number, could do it with just the letter c. Let's look at some more. Okay, so here we have a couple of a little bit more complicated looking examples. One's hiding behind me, the other one's right here. Let's take a look at this first one. The limit as x approaches some number, c, of 3x squared plus 2x minus 4. So this is a polynomial, and turns out polynomials are just combinations of a few of the things in our limit laws. Right? We have powers, we have addition and subtraction, we have constants being multiplied. And so what we can put it all together is, we know the limit of x, right? We know that limit of the identity function. It's just c. And we can then manipulate it with all those limit laws, and basically we just end up plugging in c. And this works out really well. It's really because polynomials are what we call continuous functions. That's something for later. But so turns out, and we actually have this, it's in your book, it's on page 62, that the limit of a polynomial, you just plug in the number. That's not so bad. You guys can plug numbers in. That's easy. And secondly, here's a rational function. The limit is x approaches c of 2x minus 3 over 3x squared plus 1. Here's the thing. As long as that denominator is not 0, all the same stuff is true, right? This is just a combination of powers and addition and subtraction. We have division this time. We have multiplication by some constants. And we know all of this stuff. And so again, we can just plug in the c. And that's another theorem that you'll find on page 62. And so for a rational function, if you want to take it for either of these, polynomials or rational functions, if you want to take their limits, you just have to plug in the number. Now there is a little caveat with the rational function that only works provided that the denominator is not 0. So what happens if the denominator is 0? Next board. All right, here's my next example. In this one, the limit as x approaches 2, we have a rational function, x squared plus x minus 6 over x squared minus 2x. So in this case, if you plug in 2, you have a problem. 2 squared is 4, 2 times 2 is 4, 4 minus 4 is 0. So if you have a rational function, you should probably check and make sure you know what's happening with that number that you're trying. If you can plug it in, no big deal, plug it in and just find your limit. And if you can't, then you have to do some work. So the work we had to do here is we had to factor it, because what we're going to do is we're going to remove that 0. This one has a removable 0. When we factor, we can see the x minus 2 factor on both the top and the bottom. So we make them go away. And so this limit then is exactly the same as the limit of x plus 3 over x. And so importantly, we can algebraically manipulate the inside of these limits. We plug in 2, 2 plus 3 is 5, and we get a limit of 5 halves. All right, so I'm out of time on this particular video, so I'm going to have to make a part B. So, yeah, here we go. Come back for the next one.